10.2 Earth's interior. So in section 1, we talked all about how we use seismic waves to understand what's going on in Earth's interior, what it's like. And then now in section 2, we're going to be talking about what is Earth's interior like. On this picture, it's a great picture showing us what we believe the interior of the Earth to look like. Now you'll notice there's a difference there. Why are there two different sides? It's not that we have two different Earths on the inside. It's just how we divide them up. So what you see on the left-hand side, where you see where it says lithosphere, which consists of the crust in the upper mantle, the asthenosphere, outer core, inner core, those are put into a group based on certain characteristics. And then on the right-hand side, the crust, the mantle, and the core, that's put into a group based on other characteristics. So the compositional layers, what you see on the left-hand side, crust, mantle, core, those are put into groups based on what they're made up of. What's inside of them? What elements are inside of them? Is it iron? Is it nickel? Is it magnesium? That's what those groups are made up of. So crust, mantle, core, compositional layers. I love using the analogy of a hard-boiled egg. So think of hard-boiled egg, the shell on the outside would be the crust, the mantle would be the white part of the egg, and then the core is going to be the egg yolk. It's a great little analogy. Now the mechanical layers, like you guys see on the right-hand side, those are put into layers based on characteristics that they have. What's their temperature? Are they solid? Are they liquid? So lithosphere, asthenosphere, mesosphere, outer core, inner core. So it's not that we have the Earth divided into two and it looks like it on one side and the other. It's just saying, hey, if we split it up, we can actually split it up a couple of different ways. So we're going to start on the outside and then work our way in. The crust, the outermost layer of the Earth, and it really is thin. So once again, going back to that hard-boiled egg analogy, great analogies, just like that shell is really small on the outside of the hard-boiled egg, so is the crust. So the outermost layer of the Earth. We have two different types of crust on Earth. We have oceanic crust, and then we have continental crust. Oceanic crust, just like its name implies, is found underneath the oceans. It is much younger. It is the youngest of the crust on Earth. This is where new crust is being made. Remember how we talked about mid-ocean ridges where they're splitting apart from each other on the bottom of the ocean and you have magma coming up and then it's getting pushed out. So new crust is made there. It's thinner. It only has an average thickness of 5 kilometers. The continental crust, on the other hand, this is what's found on the continents. So under us right now, continental crust. It is much older, and because it's older, it is much thicker. It has an average thickness of 30 kilometers. So if you start talking about, if I want to drill into the Earth and try to actually, get to the interior, where am I going to go? You're most likely going to start in the oceanic crust. It is much thinner. So not all crust is the same. Think of it that way. Not all crust is the same. I like this picture too. It's a nice three-dimensional picture. So once again, just showing us there's the oceanic crust found underneath the oceans. And then look at that inset picture in the upper right-hand side, continental crust, much, much thicker. The other thing you'll notice too, the reason I like this picture is it's showing us that continental crust, because it is so thick, it sinks down further. So it's heavy. Imagine like you have a boat and then you just kept filling it up with stuff and filling it up with stuff, and it's going to sink down further into the water. Same thing happens with continental crust because it is so heavy. So our next layer is the mantle, includes everything below the crust and above the core. This is the egg white. So the mantle, everything below the crust and above the core. Now the lithosphere is actually comprised, here's one of our layers that isn't a compositional, remember it's mechanical. It's the crust and a thin part of the mantle. It's hard. It is the hard part. And that's the reason why it's the crust in the upper mantle. The upper mantle is hard. Those two things together form the lithosphere, which actually makes up, which we're going to talk about in the next chapter, what we call tectonic plates. Going back to my analogy, I love hard-boiled eggs. So when you go to crack that hard-boiled egg and all those, shell pieces are still attached, it's the same thing like with our crust. You have all of these pieces on our crust. It's not one solid piece covering the Earth. These pieces are moving. Some are crashing together, some are moving away, some are sliding past each other, but that's what the lithosphere is. So our tectonic plates on Earth are the lithosphere. The lithosphere is floating on top of what we call the asthenosphere. And there's a couple of different spellings for that. Sometimes you don't see in the E in the beginning, by the way, for that. But the asthenosphere has a different consistency than the lithosphere. So whereas the lithosphere are these hard tectonic plates, the asthenosphere is what we call in geology plastic. It actually flows a little bit. We'll often talk about silly putty. If you guys ever played with silly putty before, so it's kind of like modeling clay, but the difference with silly putty is if you like make a ball out of it and you set it on the table and you come back in a few minutes, it'll actually have kind of flattened itself out. So that's what the asthenosphere is like. It's plastic, it flows. So now you have this great condition where you have these hard tectonic plates sitting on something that's already a little bit floaty, movie, plastic, and now you have this great scenario that really helps these tectonic plates move on top of Earth's crust. So the asthenosphere is the outermost part of the lower mantle. It's plastic-like, and it's what the tectonic plates float on. Finally, making our way to the inside to our egg yolk, and we've made our way to the core. So the core has a lot of heavy metals in it. So because of density, the things that were more dense, those elements that were more dense like iron and nickel, magnesium, those things settled to the middle of the earth when it was forming. The less dense elements, the things like silicon and oxygen, those are what floated up to the surface, and that's what makes up the crust. For our core, we have the outer core and the inner core. The outer core is made mostly of iron. It's liquid. It is very important to Earth because this liquid is moving. So just like we have convection currents in the atmosphere where you have warm material rising, cold material sinking, the same thing's happening in the outer core. You have this warm material rising, it's going to cool off a little bit, and then it's going to sink back down. So you have these currents of iron. And I don't know if you guys know anything about electricity or magnetism yet. When you get iron moving like that, you can create a magnetic field. This is where Earth's magnetic field actually comes from, is the outer core. And our magnetic field is really important. It's not just about us getting north, south, east, and west. It actually does some really cool things for us I'm going to talk about in a second. The inner core is made almost entirely of iron, but it's solid. It is hotter than the surface of the sun. How can that be? It's hotter than the outer core. How is it solid? Shouldn't it be liquid? The only reason it isn't, there is such great pressure from gravity pulling everything into the center, it keeps it in the solid state. If you had the ability to release that pressure, then it would turn to liquid. But because that great pressure exists there, it is kept in the solid state. So pressure is why the inner core is solid, even though it is very, very hot. So Earth's magnetic field is created by this motion of liquid iron in Earth's outer core. What's its importance besides giving us direction and a lot of other biological reasons? It helps block harmful radiation from the sun. It's sort of like this wonderful, magical, invisible layer that when harmful solar radiation is ejected towards the Earth, it blocks it. It's like a shield. So our magnetic field is actually very, very important to us. So keep in mind the different layers there that we have. So crust, mantle, core, those are put into layers based on composition, so what they're made up of, and then lithosphere, asthenosphere, lower mantle, outer core, inner core, those are put into layers based on what are their characteristics like.